Hello, I'm Seema and welcome to part 22 of the chapter Chemical Bonding and Molecular Structure. We have been discussing the molecular orbital theory and I told you about its salient features and I discussed what are the properties that are dependent on electronic configuration of the molecular orbitals. And there are three main properties, that is, you can determine the stability of a molecule, you can talk about the bond order, which also tells you about the stability, and from the electronic configuration of the molecule, you can also determine the magnetic character of the molecule. So now we come to the next step, that is writing down the electronic configuration. We will take elements of the first and the second period elements, and I'll be describing the electronic configuration based on these, that is diatomic homonuclear molecules. Diatomic, you understand, a molecule that consists of only two atoms. Homonuclear means that both the atoms are of the same element. So we'll take molecules like the first 10 elements are hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. We are going to do diatomic molecules of all these 10 and understand the electronic configuration and how the energy levels are filled up. So let us begin. The first element is hydrogen. So if you take two hydrogen atoms, let us write down the atomic orbital configuration of hydrogen. Let us take that, make two atomic orbitals. This is the 1s atomic orbital of one atom and 1s atomic orbital of the other atom. So here are the atomic orbitals, and in the middle we'll be doing these two atomic orbitals combine, we'll be writing the molecular or drawing the molecular orbitals in between. So you have two 1s atomic orbitals, and when these two combine, they result in the formation of two molecular orbitals. What would the two molecular, when we know 1s orbitals are spherical in shape, therefore when they superimpose or when they overlap, they result in the formation of two molecular orbitals. The first is the one that is lower in energy than the 1s orbitals, and this orbital would be called we would draw it like this. It would be a sigma 1s, where sigma means it's a sigma bond and sigma 1s means it's a bonding molecular orbital, which has energy lower than the energy of the two atomic orbitals. And the other orbital that you obtain, the molecular orbital, is sigma star 1s, where sigma star or sigma asterisk 1x stands for the antibonding sigma 1s molecular orbital. So these are the first two molecular orbitals that you would obtain by the overlapping of the 1s orbitals. So in the first period, we have two elements, hydrogen and helium. So let us take hydrogen and write its electronic configuration based on this is the energy level diagram, you could say, for hydrogen and helium, because both hydrogen and helium have only 1s orbitals. So in hydrogen, there is one electron in the 1s orbital and one electron here in the 1s orbital of the other hydrogen atom. So the molecular orbitals are filled up, as I told you in the previous videos. In two videos I've been telling you that the filling up of molecular orbitals is identical to that of atomic orbitals. That is, they follow the Aufbau's principle, that is, electrons first fill up in lower orbitals, and as energy level of the molecular orbitals increases, the electrons move up only after that. The second is the Hund's rule of maximum multiplicity. If you have two or more molecular orbitals which are degenerate, which means that they have the same energy, then they would first be singly occupied, that is, one electron would go to each one, and then the pairing would begin only after each degenerate orbital has been singly occupied. So we find that we have these two electrons. So how would you fill up the molecular orbital? The molecule now has two electrons, one from each hydrogen, and these two electrons would go to the lowest orbital. So here in sigma 1s we have two electrons, right? So this was the hydrogen molecule, and what would its configuration, molecular configuration be? H2 molecule has the molecular orbital configuration of sigma 1s2, right? From this, what do you understand? We see that we can determine the stability. How do you find out the stability? If the number of electrons in bonding, if Nb is greater than Na, the molecule is stable. We see that there are 2 electrons in the bonding orbital and no electron in the antibonding molecular orbital. Therefore, Nb is greater than Na and hence this molecule is stable and it exists. The second thing that we can determine from it is its bond order. How do you calculate bond order? Bond order is equal to half of Nb minus Na. So bond order is, for hydrogen, bond order would be half of Nb, number of electrons in bonding is 2, minus 0, which is equal to half of 2 would be 1. It has a bond order of 1, which means that there is a single covalent bond between these 2 hydrogen atoms. And the next thing that we can determine from its configuration is that if all electrons in the molecular orbitals are paired, then the molecule is diamagnetic in nature. But diamagnetic means it is weakly repelled by a magnet. But if the molecule is such that it has unpaired electrons, then the molecule is paramagnetic, which means that in the presence of a magnet, it turns magnetic, or it is attracted to the magnet, or in the presence of a magnetic field, it has magnetic properties. And on removal of the field, it may go back to being non-magnetic. So from this we see that there are only 2 electrons and they are paired. Therefore, this molecule should be diamagnetic in nature. So hydrogen should be diamagnetic. Right? Now we take the next element. After hydrogen, we have helium. Helium has 2 electrons in the 1s orbital. This is one helium atom and this is the other atomic orbital of the other atom. So helium here has 2 electrons, right? So we are now considering He2 molecule, helium molecule. So here it has 2 electrons, we have 4 electrons now. So how would the orbitals be filled up? 2 come to sigma 1s and the next 2 electrons go to sigma 2s. Why? Because first, according to Aufbau's principle, the lower orbital, the orbital having lower energy fills up first and then the orbital having higher energy fills up. Therefore, this is what would the configuration of He2 molecule be then? It would be sigma 1s2 sigma star 1s2, which means it has 2 electrons in the bonding molecular orbital and 2 electrons in the antibonding molecular orbital. There is one thing that I would like you to always keep in mind, that when such a division occurs, when 2 atomic orbitals having the same energy, they distribute their energies to form 2 molecular orbitals. The bonding molecular orbital goes down in energy and the antibonding orbital goes up in energy. Whatever amount of energy the bonding molecule goes down in, that is what the amount of energy that decreases when a bonding molecular orbital is formed, the same amount of energy increases when an antibonding molecular orbital is formed. Why is this? Because the sum of these 2 should always be equal to the sum of the energies of the atomic orbitals. So if we say that this has gone down about whatever little bit of energy, the same amount of energy increase. If this went down this much, the same amount of energy should go up for the antibonding molecular orbital. If this decreased this much, the energy of the antibonding molecular orbital should increase by an equal amount, so that the sum of the 2 comes out to be equal to the sum of the 2 combining atomic orbitals. Right? So the stability that is provided by the bonding molecular orbitals, the electrons in the bonding molecular orbitals, is equal to the instability created by the electrons present in the same antibonding molecular orbital. Now in He2, we have 2 electrons which are contributing towards the stability of the molecule and 2 electrons which are in the antibonding molecular orbital, which are making it equally unstable. So do you think there is a difference between 2? There are 2 atoms. Why do atoms combine? They combine to become stable. So if helium is not acquiring any stability, the amount of stability that it is gaining in the bonding molecular orbital is equal to the amount of instability it is getting from the antibonding molecular orbital. So why would the molecule be formed at all? Energetically, it's not feasible. There's no point making the effort when you're not getting any result at all. There's no stability that you are acquiring. So we see that He2 molecule from this itself we can see should not exist. How? The Nb is not greater than Na. Right? Nb and Na are equal. Number of electrons in bonding and antibonding is equal. If Na was greater than Nb, even then the molecule would have been unstable. But in this case, anyway, it is Nb is not greater or Nb is equal to Na, therefore it is unstable. The next thing, what would the bond order be? We know positive bond orders, if they are present, then the molecule exists. But if the bond order, when you calculate it, comes out to be 0 or negative, then the molecule does not exist. And the bond order here would be half 2 minus 2, because number of electrons in bonding minus number of electrons in antibonding is 0, therefore bond order is 0. So bond order also tells us that this molecule does not exist. And since this molecule does not exist, there is no point discussing its magnetic character. So these were elements of the first period which only have the 1s orbital. We now come to elements of the second period. In the second period, this filling up has already taken place. Let us take the example of lithium. Lithium has 3 electrons. So now what would the configuration of lithium be like? Lithium has 3 electrons, which means that 1s, the 2 electrons, there are 2 lithium atoms, 1s, 2 electrons in 1s orbital and 2 electrons in 2s orbital. 1 electron in 2p orbital. So lithium has these 2 orbitals, that is 1s here and 1s here, and this is 2s of one atom and 2s of the other atom. Each lithium has 3 electrons, so it has 2 electrons in 1s and 1 electron in 2s, and here 2 electrons in 1s and 1 electron in 2s. So now 2s would also result in the formation of 2 orbitals, that is the sigma 2s and the sigma star 2s, right? So the situation is the same now. In lithium, the first shell is already complete. That is, this is the core of the atom. We have studied in atomic structure that the core, that is the nucleus and all the penultimate shells, which are not the valence shells, they form the core of the atom, and the outermost shell forms the valence shell. So the core is already completed. The 2 electrons in 1s and 2 electrons in 1s of both the lithium atoms, they fill up the sigma 1s and sigma star 1s molecular orbitals. And now we come to the 2s orbitals. So 1 electron each, what would the configuration be? The configuration of Li2 molecule would be sigma 1s2, sigma star 1s2, right? Sigma 1s2, sigma star 1s2, and then we have sigma 2s2. Do you see this? Now what would the bond, would it be stable? Nb, is it greater than Na? We see what are the number of electrons in bonding? 2 plus 2. We have 4 electrons in bonding. And how many electrons in antibonding? We have only 2. So the value is plus 2. Therefore, yes, this molecule does exist. How would you calculate the bond order? Bond order would be equal to half Nb minus Na. Right? So this would be equal to half of 4 minus 2. Which is half of 2 is equal to 1. So this bond order 1 shows that Li2 molecule exists, it's a stable molecule, and there the bond order 1 shows that there is a single covalent bond between 2 lithium atoms to form a lithium molecule. So let us now come to one more thing. When you're writing down the configuration and the core is completed, you can write for the core, you can write KK, where KK means it's the closed kernel. Closed kernel. The kernel, that is the core, is already completed. The configuration of the core is completed, and K is the kernel and K we use for completed, KK. And then we write the valence shell or configuration. So lithium Li2 would be KK sigma 2s 2. Right? So this is how we write the configuration of elements which are in which the kernel is already completed. Now let us look at beryllium, Be2 molecule. Right? For beryllium 2, beryllium has 4 electrons, 2 in 1s and 2 in 2s. So now beryllium has 2 and a situation similar to helium arises. The molecular orbital will have these. Now we have 8 electrons. So how would the molecular orbitals be filled up? 2, 2, 2 and 2. So how would you write Be2 molecule? The configuration would be, let's write KK. KK is for this, which we don't have to write. And then sigma 2s has 2 electrons and sigma star 2s has 2 electrons. So this is the configuration of beryllium. Now Nb, in KK, the Nb and Na are equal. So what would the stability be like? Nb is greater than Na? No, Nb and Na are equal. When they are equal, it means the molecule is unstable, its bond order would be 0, molecule does not exist, no point discussing its magnetic character. So this was beryllium. Now after beryllium comes boron. In boron, what is the configuration of boron atom? Boron is the 5th element, so the configuration is 1s2, 2s2 and 2p1. Isn't it? This is the configuration of a boron atom. Now what I'll do is, I'm going to wipe off this portion and we'll turn this into the second shell, so as to have the closed kernel is understood, so that I can draw the p orbitals here. So let me just wipe this off and assume that this 1s is under the board and this now is the second shell. So this would become, this is 2s, this is 2s, this is sigma 2s and this is sigma star 2s, right? And when you have 2s with boron, actually, right. So boron has, we know the p orbitals, that is 2p orbitals. There are 3 2p orbitals and they are degenerate, the atomic orbitals. So I'll make 3 2p orbitals here for one atom and 3 2p orbitals for the other atom. Right? This is 2p, or I can label them as 2px, 2py and 2pz. And here I'll reverse the order. I'll tell you why I did that. This is 2pz, 2px and 2py. Right? Now what would you expect the energy level to be like? If you remember, when we discussed the bonding of the p orbitals, I told you that the z-axis is the internuclear axis. And the px and py orbitals, even when we did hybridization in the VBT, we talked of px and py not participating in hybridization when multiple bonds are being formed. So the first bond between pz and pz should be a sigma bond, because the pz is the internuclear axis. But after the sigma bond is formed, the px and py would overlap sideways and result in the formation of pi bonds. The amount of overlap of sigma bonds is more because it's a head-on overlap. The entire lobe can merge in the p orbitals. You have 2 lobes. So the entire lobe, when it is head-on, the entire lobe can merge into the lobe on this side. But in px and py, which are sideways overlapping, first of all, the repulsion of the electrons in this would not allow these to come very close or easily come close to each other. And the area of overlap is only a little bit on top and a little bit in the bottom, sideways. It's not head-on. So the overlap of p orbitals, that is px and py, to form the pi bonds is not so effective. As a result of which, the energy of the p orbitals is higher. And if the energy of the p orbitals or the pi bonds is higher, you would expect the energy of the 2pz and 2pz when it forms the bond. The 2pz and 2pz will form sigma bond, while the 2px and 2py are going to form pi bonds. And the energy of sigma bond, you would expect it to be lower than the energy of the pi bonds. Logically, because the overlap, the extent of overlap in sigma bonds is much more than the extent of overlap in pi bonds. So our logic tells us how should the energy level diagram be for the 2p orbitals. We say that 2pz and 2pz should form a sigma bond. So they will form a sigma 2pz bonding orbital, right? And whatever is the decrease in energy, it should be equal to the increase in energy for sigma star 2pz. This makes sense? Whatever energy decreased, it should be equal because the sum of these two should be equal to the energies of the sum of the two atomic orbitals, right? Now, the 2px and 2py, they form pi bonds, but they should be degenerate. They should have the same energy. So, the 2px and 2py should come here and they should form two orbitals here, and the same energy should increase here, and these should form the pi star. So, this is pi 2px and this orbital is pi 2py. Here it will be pi star 2px. And this would be pi star 2py. Am I clear? Now this is what we would expect the energy level diagram to be like, right? Logic tells us that this should be the diagram. But what do we actually find? We actually find that in elements like boron, carbon and nitrogen, boron, carbon, nitrogen do not have this distribution. They have an abnormal configuration. You would expect the sigma bond to have lower energy and the pi bonds to have higher energies, but in boron, carbon and nitrogen, this orbital does not have lower energy. It has energy higher than the pi bonding orbitals. The energy of the sigma 2pz orbital is higher, sigma 2pz orbital gets higher than the pi 2px and pi 2py bonding molecular orbitals in three elements, that is boron, carbon and nitrogen. The reason for this abnormal configuration here is that there is orbital mixing in these three elements. Now, how would you understand what orbital mixing is? Let us assume that you have the second block, the second period elements, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Okay? Now what happens in lithium, the energy, in lithium you have only the s orbitals. With boron you come with the p orbitals. In lithium you have 1s energy and 2s energy. Beryllium also has 1s, 2s. Its 1s would be boron, 1s, 2s. And boron now has 2p, 1 electron in the p orbital. So this is the energy of the p orbital. In carbon also, if this is 1s, this is 2s and this is 2p. And in nitrogen also you have 1s, 2s and 2p. In oxygen you have 1s, 2s, 2p. Fluorine and neon. This is just a hypothetical energy difference. I'm just assuming this. What we notice is that in boron, carbon and nitrogen, the energy between the 2s and the 2p orbitals, 2s and 2p orbitals, this is 1s. We are not really concerned about that. The 2s and 2p orbitals in boron, carbon and nitrogen is not gigantic. And if the difference is not gigantic, you know that electrons sometimes, the orbitals, they can mix, as we studied in hybridization also, that when the orbitals have energies which are kind of comparable, there is a chance of them mixing. In boron, carbon and nitrogen, the difference of energy between the 2s and 2p is not very high. As a result of which, these mix. And the result of this mixing or this confusion is that the sigma 2pz orbital becomes higher in energy than the pi 2px and pi 2py. Right? It becomes higher in energy. While logically we expected the sigma 2pz to be lower in energy than the pi because the sigma bond is stronger than the pi bond. Yet this abnormal jump, but nothing happens to the sigma star. It remains where it is, its energy level. This little abnormality in these three elements is because of the orbital. We call it the 2s 2p or sp orbital mixing. The reason for it is the sp orbital mixing. And what happens when you come to oxygen, fluorine and neon? Why don't they have orbital mixing? Do you notice that the p orbital suddenly starts gaining a lot more energy, or we could say the energy difference between the p orbital and the 2s and the p orbital increases. It increases so much that now there is no possibility of a mixing of these orbitals. What is the reason for this increase? That as the number of protons in the as we move from left to right in the periodic table in a period, the number of protons is increasing. Therefore, nuclear charge is increasing. As nuclear charge increases, the size of an atom decreases. You are aware of that. And since the s orbitals are spherical in shape, the effect that is felt by the s orbitals is much greater than the effect felt by p orbitals, because p orbitals are directional and s orbitals are spherical. So the s orbitals of oxygen, fluorine and neon, the 2s orbital, it comes much closer to the nucleus. And the closer the orbitals come to the nucleus, the more stable they become. The lower is their energy. At the same time, the p orbitals cannot penetrate so much. And therefore, the p orbitals, their energy increases as it should increase, but the 2s orbitals energy, due to the decrease in size, it comes closer and closer and decreases the energy of the 2s orbital. As a result of which, orbital mixing is not possible, so that's not a factor. You would get the configuration that you would expect, the normal configuration. I hope I'm clear about this. So now that we have understood about orbital mixing, let us come to the element that we were concerned about, that is boron. So if we now write the configuration of B2, right? B2. Boron has how many electrons? It is the fifth element, so it has 1s2. 1s2 I told you is already filled up. 2s2. So we fill up 2s2. And it has 2p1. It has one electron in 2pz. Or we should not write it in 2pz because it is actually going to come down here. Now, since the pi bonds are going to be more lower in energy. So, what would you expect now the molecular configuration to be? It would be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Now we have 8 electrons and 9 and 10. These 2 electrons would go to pi 2px. Follow Hund's rule of maximum multiplicity. When you have degenerate orbitals, the electrons will first singly occupy the degenerate orbitals and only then the pairing would begin. So the configuration here would be this. So how would you write the configuration of B2 molecule? B2 would be KK. KK is the closed kernel for the 1s orbital. Then you have 2 sigma 2s 2, sigma star 2s2, and then we have pi 2px1 and pi 2py1. Do you see? So the molecular orbitals, now instead of sigma 2pz being filled up here, it is pi 2px and pi 2py, which would be singly occupied. How does this affect the molecule now? As far as stability is concerned, how many electrons are present in bonding and antibonding? Let us just ignore, they should be greater. So let us just ignore the kk. Here you have how many electrons in bonding? 2, 3, 4. 4 electrons in bonding, 4 minus 2 electrons in antibonding, right? And if you really consider the kk also, this would be 6 minus 4, because there were 2 electrons in bonding and 2 electrons in antibonding in the first shell. So 6 minus 4 is plus 2, and if you have half of this, you will get the bond order. So half of this, half of 2 would be 1. Therefore, such a molecule exists, and there is a single bond between the 2 boron atoms. And what would you talk about its magnetic character? I told you, if there are unpaired electrons in the molecule, then the molecule should be paramagnetic in nature. And it has been found that the boron molecule does exist and it is paramagnetic in nature. So after boron, the next atom is carbon, right? So let us see if we have a C2 molecule. So carbon is the 6th element, 2, 4, 5 and 6. You would now have 2 electrons here. And where would these 2 go? They would go here to these pi 2px and pi 2py, and therefore the configuration of C2 would be this. So let us see what the configuration is like. It would be kk, sigma 2s2, sigma star 2s2, and then you have pi 2px2 and pi 2py2. Isn't it interesting? Now this is the configuration of carbon molecule, the molecular orbital configuration. What do we notice from here? That all the electrons are paired. This is one thing that we notice, right? That all electrons are paired. And one very strange thing that you notice is that you would expect a sigma bond between 2 carbon atoms. Instead, it has 2 pi bonds only. It does not have a sigma bond. So it has 2 pi bonds. This is a strange thing that you would observe in a carbon molecule, isn't it? So it has 2 pi bonds, and since all the electrons in the molecular orbitals are paired, what would its magnetic character be like? It would be diamagnetic in nature, because it would have been paramagnetic if they were singly occupied electrons, electrons which were occupying orbitals singly. So this would be diamagnetic. Would it exist? Would the molecule exist? Let us count. kk is 2. How many atoms, electrons in sigma in bonding molecular orbitals? 2 plus 2, 4. 4, 5, 6, 7, 8. There are 8 bonding minus how many antibonding? 2 plus 2, 4. There are no more. 8 minus 4, which makes it 4. And the bond order would be half of this. BO would be half of this. Half of 4 would be 2. So this shows there is a double bond between the 2 carbon atoms, and this double bond is, both the bonds here are pi bonds, right? So that was a carbon molecule. The next element that we come to is nitrogen. In nitrogen, you know, we have 3 electrons in the 3p orbitals. What is the configuration of nitrogen? 1s2, 2s2, 2p3. Right? So we have 2 nitrogen atoms, and now we have 2 more electrons. So now nitrogen has 3 electrons here in the p orbitals. So if there are 3 plus 3 is 6. So 2 plus 2 plus 2 will come here. So we have, what would the configuration of nitrogen molecule be now? Let us wipe this off. Come to nitrogen. N2, right? The configuration would be kk, sigma 2s2, sigma star 2s2, then we'd have pi 2px 2, pi 2py 2, and sigma 2pz 2. This is the configuration of nitrogen molecule. Now, when you have this as the configuration, let us calculate the bond order, and we get the stability from it. Half Nb minus Na, right? So it will be half. How many electrons are there in bonding? 2 plus 2, 4. 4, 5, 6, 7, 8, 9, 10. There are 10 electrons in bonding. And how many in antibonding? 2 plus 2, 4. Only 4. 10 minus 4, which is 6. So this would be 3. Bond order is 3. And we know that in nitrogen, there is a triple bond between the two nitrogens. 2 pi bonds and 1 sigma bond. Right? So this was nitrogen molecule. And what about its magnetic character? All electrons in the molecular orbitals are paired. Therefore, this molecule should be diamagnetic in nature. And we actually find nitrogen molecule to be diamagnetic. Right? So now nitrogen is the last element till which orbital mixing takes place. And you find that the energy of the sigma 2pz is actually greater than pi 2px and pi 2py. With oxygen, orbital mixing ends and we get the configuration as expected, that is the sigma 2pz should have energy. This is sigma 2pz should have energy lower than the pi bonds. So with oxygen has one more electron in it. So let us put it here, one electron here, and let us put one here in Y. It's just, convention. Automatically now we have 2 more electrons here in the molecule. Where would those 2 electrons go? They would go into the pi star 2px, and due to Hund's rule of maximum multiplicity, both of these orbitals would be singly occupied. Right? So let's write the configuration of oxygen. The configuration of oxygen would be Kk, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, pi star 2px1, and pi star 2py1. Right? So if this is the configuration of oxygen, what would you judge about its stability, the bond order? Let's calculate the bond order. Bond order is half Nb minus Na. So this will be equal to half. What is the number of bonding electrons? 2, 4, 5, 6, 7, 8, 9, 10. So there are 10 electrons in bonding orbitals. And how many in antibonding? 2, 4, 5, 6. So 10 minus 6 is 4. And half of that will be equal to 2. Which means there's a double bond between the two oxygens. A bond order of 2 means that there's a double bond between the two oxygens and the molecule is stable. And what do you know about its magnetic character now? There are 2 single electrons, that is unpaired electrons. Therefore, this molecule should be paramagnetic. Right? So let us now come to the next molecule. After oxygen, you have fluorine. So in fluorine, we'll put 2 more electrons. 1 electron here and 1 electron here. Now this is the 9th element. And when you have 2 more electrons in fluorine, what would happen? Where would you fill up these 2 more electrons? They would go, and since they would go to these degenerate orbitals, and the pairing would begin. So the configuration of fluorine F2 now would be Kk, sigma 2s2, and here instead of 2px1 and pi 2py1, you would have pi star 2px2 and pi star 2py2. And in the bond order, what would the bond order? You'll add 2 in the antibonding molecular orbitals. So this would be 10 minus 8, and therefore you would have 1. Bond order would be 1. And how about the magnetic character of fluorine molecule? All electrons in the molecular orbitals are paired. Therefore, this would be diamagnetic. Right? Also, we know that fluorine belongs to the 17th group and it has 7 electrons in its outermost shell. In order to acquire stability, it shares 1 electron with a neighboring fluorine atom, thereby forming 1 covalent bond. And that is also seen in the bond order, and you can see that from the configuration also. So now we come to the next element, that is, after fluorine you have neon. In neon is the 10th element. You have 6 electrons in the p orbital, right? So now the second shell is also complete. And where would these 2 electrons go? They would go to sigma star 2pz, right? And this time again we get a configuration where the number of electrons in the bonding orbitals is equal to the total number of electrons in the anti-bonding molecular orbitals. So what would the configuration here be? In addition to this, it is kk, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, pi star 2px2, pi star 2py2, and in the end you will have sigma star 2pz2. That is neon molecule now, right? Neon is a noble gas, and if we calculate the bond order, this would be 10 minus 10. Half of 10 minus 10 is 0. Therefore, such a molecule would not exist, right? And if such a molecule does not exist, if it has a bond order of 0 and the molecule does not exist, there's no point discussing about its magnetic character. With that, I come to an end to this video. If you found this video helpful, please give it a thumbs up and subscribe to my channel, share it with your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.